Okay, this is lesson 2.2 on limits involving infinity. So what we're really looking at is the end behavior of our graph here. So as the ends of our graph is approaching infinity on the right-hand side, and as the graph is approaching negative infinity on the left-hand side, where is my graph going towards? So it doesn't matter if your graph crosses the horizontal asymptote a couple of times. Again, the asymptote is kind of a misnomer here. We're really looking at the end behavior at the ends of your graph towards infinity, towards super, super far. Where is this graph approaching? And same as the previous lesson, we're really looking for a numerical value. So if it does truly have a horizontal asymptote or an end behavior, it's going towards a single number, whether it be 0, -4, 2006. These are numerical values. So same rule as before, because these are numerical values, I can add or subtract or multiply by a number or divide or take it to a power, all these limits, because they are just numbers and we can do these operations on them. Okay, so just a reminder that if it is going towards infinity and head to the same number as it is heading towards negative infinity, it is also called a horizontal asymptote, right? And then you have a vertical asymptote if your graph, when it's approaching from the positive side, is going up to infinity or going down to negative infinity, and vice versa, going down to negative infinity, up to positive infinity. You have these vertical asymptotes. Yeah, okay, so those are very thick lines that I have here. Okay, all right, so let's take a quick look. It says, use graphs and tables to find a limit as x approaches infinity and limit as x approaches negative infinity, and identify all horizontal asymptotes. So in the first one, zoom in for you, I have a t-table here and I have a graph here. So notice how my scale is not super big, but you can already see that this graph, with the behavior of it, where is it going towards, it is plateauing out and is flattening out over on both sides, right? If I use a t-table, you see I try to get big, not super big, but you can kind of get the idea that as it's going towards -3000, it's at -1.4257 times 10 to -4. So that's -0.00014257. You can see that's a lot of zeros, and it's just going to go on and on and on, right? Same thing with the 3000. If I were to go bigger on the other side, it's going towards 0.0000 something as well. So what that concludes for us, based on the table and the graph here, is that the limit as x approaches infinity, as it's going towards a big number, it's heading towards 0. And as it's going towards negative infinity, it's also going towards 0. Because they're going towards the same number, we have a horizontal asymptote at y equals 0. Okay. All right, number 2, we graph this out. This one, it took a while to zoom out to look at this, but this is the way the graph goes. So as the function is going towards negative infinity, it's going up to a really big number, so it's going towards infinity. And as it's going towards positive infinity, it's also going towards infinity. You can see the number got super big, and it's going to get bigger and bigger and bigger. So what is happening here? We have limit as x approaches infinity is going towards infinity. So limit as x is going out this way, my y value is going up to infinity. Limit as x approaches negative infinity, going out this way, is going up to positive infinity again. Now, even though they're both going towards infinity, they're going towards infinity at a different rate, and they're not really going towards the same infinity. It's, yeah, a little confusing there. They're not going towards the same number. Hence, part C will be the answer of no horizontal asymptote, and your graph proves that to you as well. Okay. All right, next, limit as x approaches 2 from the left-hand side, right? This has a negative here from the left-hand side. So I graph the function out. I have some asymptotes here, as you can see. And so 2 is right here. Notice how I look at 2 from the left-hand side, so any number that is smaller than 2. So going towards it, what is happening? We'll start from a -5, go up to -7, to -9, to -12, to -19, to -39. So yeah, it's getting big, but not that much bigger. That's because the difference between the number prior to the 2 is not significant enough. If I make my t-table 1.99999, you'll see this number is going to be a negative, big number. So we can conclude that as x is approaching 2 from the left side, look, the graph proves it to us, we are heading towards negative infinity. So my limit is going towards negative infinity. Now, don't forget that you can find vertical asymptotes very easily using the same idea here too. But right now, I can also remind myself that, hey, I can take this x minus 2 on the bottom, set equal to 0. That will give me my vertical asymptote at x equals 2. Okay? All right. same with the next one. This is called a greatest integer function. So INTX is the greatest integer function. That means whatever X value you plug in, you basically drop off the decimals and keep just the whole number. This is what we used to call the step function. It kind of looked like this, but because of the extra X there, it's changing its face. So it's looking a little bit different this time, right? So as you can see, I'm going towards 0 from the left side. So this graph is going up this way. I'm going to assume that it's going to go up to infinity. And let's see if my t-table will help me. All right, so here's 0. I'm coming from the left side here. And notice the number got bigger and bigger and bigger and bigger. Now, it doesn't look like it's getting gigantic, but again, same as before. The difference between the 0 and the number I picked before isn't that significant. So that's why this 20 doesn't look gigantic. So if I were to put in negative 0.000000001, then that number would be a big, giant, infinitely bigger number, right? So limit as X approaches 0 from the left-hand side is going to be infinity. And as you can see in this picture, there's no vertical asymptote because there, one side is not going towards the same thing as the other side, okay? Well, sorry, that's a different thing. So you can see in this picture, there is no vertical asymptote. I was thinking horizontal asymptote. Apologies. All right, so find the vertical asymptotes of the graph. Describe the behavior from to the left and right of each vertical asymptote. So I reminded you here that, hey, to find vertical asymptote, simply take the denominator, set it equal to 0 to solve for vertical asymptote, because when the denominator is equal to 0, that's when we have these really weird values and really weird behaviors, right? So the first picture here in part A, I'm going to find the vertical asymptote by setting my denominator equal to 0. So 2x plus 4 equals 0. Set it out and you get x equals negative 2. That is my vertical asymptote here in the picture. Now, I graph this out and I can see to the left of it, to the left side of it, my graph is going down towards negative infinity. To the right of it, I'm going up towards infinity. So how do I write that? Limit as x approaches negative 2, that's my vertical asymptote, from the left-hand side. So from negative 2, from the left-hand side, I get negative infinity. So from the left-hand side, I get negative infinity. I'm approaching negative 2 from the positive side. From the right-hand side, I'm going up towards positive infinity. And so that's how you describe the behavior to the left and right of your asymptotes. So this is secant x. Number 6 is secant x. What is secant x really? Secant x is really 1 over cosine x. So now I can go ahead and set my denominator equal to 0. So when is cosine equal to 0? Well, cosine is equal to 0 at pi over 2, 3 pi over 2, both positive and negative. So that's why you see in this picture, I have lots and lots of asymptotes. I have negative 3 pi over 2. I have negative pi over 2. I have positive pi over 2. I have 3 pi over 2. Now notice some of these have the same behavior. So which ones? Well, this asymptote and this asymptote has the same behavior to the left and right. To the left, I'm going down towards negative infinity, down towards negative infinity. To the right of it, I'm going up towards positive infinity, up towards positive infinity. So what is the pattern here? It goes negative pi over 2. I gotta skip 1. 3 pi over 2. Skip 1. So I'm gonna guess it's gonna be 7 pi over 2. Skip 1. So I'm gonna be 11 pi over 2. When I say skip 1, it's really not skip 1. You can see the difference here is 4 pi over 2. So it's 2 pi. So if you add 2 pi increments, you get the same behavior. Same thing with the other side. If you look at it, this asymptote has the same behavior as this asymptote, right? The behavior of it is going up towards positive infinity and then going down towards negative infinity. And this went from pi over 2 to negative 3 pi over 2. Again, 2 pi increments. So this is a good way of writing it, right? So if I take pi over 2, which is this one right here, and I add all 2 pi increments, where n is an integer. This is a notation of it's an integer. So the left side of it will go towards positive infinity. The right side will go towards negative infinity. So then if I were to look at this one, this is the 3 pi over 2, and with 2 pi increments, the left side actually is opposite. It's going to go towards negative infinity, and the right side is going to go towards positive infinity. So again, take a minute, kind of let that sink in a little bit on how to write these notations. If you don't want to write it this way, it's totally fine. It's just going to be a lot more explanation if you write it a different way, and it's harder to understand. Okay? All right. Moving on, we have find a limit as x approaches infinity and as x approaches negative infinity. So again, it's really looking for end behaviors here. So when it's a really messy function like this one in number 7, what I recommend you to do is go ahead and combine it into one single fraction. Because once you combine it into one single fraction, the highest power polynomial is what determines your end behavior. So that's what I did here. I first go ahead and combine them into one single fraction and one single fraction on each side. Then I multiply the whole thing out. Then I simply look at the highest power and the highest power. So then when I reduce it out, I get a single 5. And that's the only number that will affect your end behavior. So as it goes towards positive, negative infinity, my value is going to be 5 because that is my horizontal asymptote as well. Okay. When it's a trig function, you have to separate it. So you can separate this as 2x over x and then sine x over x. In the previous lesson, we know the limit as x approaches 0 of this function is going to be 1. But what is the limit as x approaches infinity of that function? If you recall, this is one of the weird functions that oscillates and flattens out, oscillates and flattens out. So as it goes towards 0, as it goes towards positive and negative infinity, my limit is 0. So this one is going to head towards 0. This one is going to head towards, when you reduce out the x, it's going to head towards 2. So this is my algebra here. I go ahead and solve this out, clean it up, and you will see that the limit approaches 0. This reduces out to 2. So the horizontal asymptote or the end behavior of this particular function is going to be a positive 2. Okay. All right. Next, find a power function end behavior model for f, which just means find the highest degree function here, and that's going to be your end behavior. That is going to be what is modeling. So the highest power here dictates everything. Negative 4x cubed here is going to dictate the behavior of this function because that x squared and that 2x back there, it's not going to do a lot because the x is not powerful enough, literally, to make any difference in this function, right? And then identify if there's any horizontal asymptote. Well, number 9 here, there is no fraction, therefore there is no horizontal asymptote. Horizontal asymptotes only happen if you have fraction or rational functions, and only when the top degree is equal to the bottom degree or top degree is smaller than the bottom degree. So you will see the model is going to be that negative x to the third. And if you recall, the end behavior is going up towards the left and down towards the right here, up towards infinity, down towards negative infinity because it's a negative odd function. There's no horizontal asymptote because there is no fraction here. Okay. Same thing in the next one. Because it's a rational function, I simply look at the highest power over the highest power. I clean that up. I get the end behavior model be negative x squared. This is a negative even function, so it goes down towards negative infinity on both sides. And once again, because the difference is more than 1, right? So actually, it has to be either the same degree or the top has to be smaller. So because the top is bigger, then there is no horizontal asymptote as well. Okay. Okay, so right now we're being asked, number 11 here, to find a simple basic function as a right end behavior model, and we're looking for left end behavior model. So what you want to do is look at your original function, look at the terms, and see which one is a better end behavior model for your entire function. So this entire function is x squared plus e to negative x. You want to look at x squared and e to negative x respectively and see which one is a better fit for your left side or right side, right? So if you use a calculator to graph this out, the red one here is actually my original function. This is y. This is the original f of x, right? So this is your original function. And then when I map this out, I actually have y equals x squared right here. And it actually is on this side as well because it's x squared. But you can see that it matched really beautifully on the right-hand side. So that's my right end behavior model. When I map out e to negative x, is actually this one right here. And you can see it is a very good behavior model for the left-hand side. Even though they don't match up perfectly, we can see they're kind of parallel to each other, going towards the same idea. So the right-hand behavior model is y equals x squared. The left-hand behavior model is going to be e to negative x. Now, sometimes it doesn't work so beautifully. So on the other one, you'll see in number 12 here, I have my terms. I have my single terms of x squared and sine x. So when I graph out x squared equals x squared plus sine x, I get the red function here. Right? The red function here is my original function. This is x squared plus sine x. And then I map out x squared. You can see x squared matches pretty nicely on the left-hand side. A little bit lopsided, but also matches out pretty nicely on the right-hand side. And sine x is just kind of lonely down on the bottom here. Not doing anything for it. So it doesn't match up. So sometimes one of the functions is both the right and left end behavior model for the function here. So if you want to take a minute, you can see the algebra or the calculus behind these to show you the limit and show you how they become 1 and to prove that it is the end behavior model for each of the functions. So this one is for the left end behavior, right end behavior model for number 11. And this one is for number 12 since only one of them match up nicely. Okay, all right, that's it.